today, or do you guys want to have your lecture on Thursday? Can someone please inform me? Group 5. Hello?
So
Anyone from Group
sorry,
5 here?
can you repeat the question? I didn't hear clearly just now.
This week, there's no graph lecture, graph lab. There's no lab for graph. Okay, so do you guys, I forgot actually, I thought there was lab. So there's no lab on graph. So would you guys want to make your lecture today at 10, or do you guys want to make another lecture for your group, which is on Thursday?
Oh, it's okay. We can. For me, I think it's okay to have lecture today.
Okay, others who don't want to have lecture today, can you please inform me in a few seconds? So you guys okay? If everyone agrees, don't say anything. So can I assume that it's okay to have lecture today? Okay,
Yes, okay.
All right, okay. So if okay, group 5, please take your attendance first, only for group 5, not group 6, Group 5, take attendance first. Only group 5, yeah? Group 5, please take attendance first, yeah? Okay, group 6, please take your attendance. We start our class at 10, 10, 10, yeah? You see how many people have registered first? 22, 27. We start our class at 10:15. I think there's a few people still haven't joined. Okay? 10:15, we start our class, yeah? Anyone haven't taken the attendance? Please inform me. I don't know what you're talking, Nabil Hafiz. What's the issue? Cannot take attendance or what? No idea. Nabil Hafiz, I do understand your message. Why need manual attendance, Nabil? Nabil, why do you need manual attendance? You're not supposed to be outside next time during class. You're what group, Nabil? You need to tell me your group number as well. Okay, we start our class.
Okay, sir.
Can you guys? Okay, all right. So our topic today will be on graphs, yeah? So you're gonna learn about the graph, the terminal and the basic concept of graph. And then you look at how you present graph in computer memory lah. Okay, so there's two methods. Either you use matrix or you use a linked list. Alright. And then we're gonna look at two types of graph traversal algorithm, which is deep in search and breadth in search. Okay. So this is basically a graph. A graph consists of vertices, the circle one here, and then the edges, the connector. So when you talk about edges, there's two types, directed and undirected. So this one is undirected lah. Okay. So it's just a graph. This is not a directed graph here because there's no arrow here. Alright. So the basic concept you already learned also inside your discrete mathematics. So this is the notation for a graph. It consists of vertices and also edges. Alright. So the elements of E are unordered pairs because why? There are no arrows. If it's an ordered pair, it has arrow like this one here. Okay, so this is an unordered pair. Alright. So the pairs UV and VU represent the same edge. So here there's a pair 1, 2 or 2, 1. Pair 3, 4 or 4, 3. Okay, any questions so far? So this is the concept lah for undirected graphs or unordered pair. This is a concept for directed graphs or known as digraphs. Alright, the elements are in ordered pairs. Okay, there are two notations here. Here means the vertices in graph 1. Here means the edges in graph 1. So these are two things are different, yeah. So these are, again, I repeat, the vertices. So what are the vertices in G1, graph 1? 1, 2, 3, 4, 5. So the elements are 1, 2, 3, 4, 5. Elements in graph 2 is 0, 1, 2, 3, 4. So you get this one here. And then this one is for graph 3. Now, the edge is, however, is basically the connector between the two vertices. In this case, it is ordered. Why is it ordered? Because of this arrow here. So, the edges in graph 1, so you must learn how to write this one here. E means edges here. Dalam kurungan, inside the open close bracket here is G1 here refers to the name of the graph. The elements are an ordered pair. You don't forget to do this one now. Open close curly braces. Each edge is within an ordered pair. The order is 1, 2. Okay? 1, 4. So you get like this one here. 2, 5. And 3, 1. 3, 4. And 4, 5. Any questions? No question. Got questions? Please ask now. Concept.
No question.
No question, yeah? Okay. Then we have the next one, we have a subgraph. So for something to be a subgraph, so if, for example, you say this subgraph B is a subgraph of A, all the vertices in subgraph B must be, okay, a subset of subgraph A, okay, or graph A, and the edges must also be a subset of graph A. Okay. So to be a subgraph, every vertex of H is a vertex of G, and every H in H is an H in G. So what do we mean by when we say adjacent vertices? Okay, adjacent vertices are basically vertices that's connected by an edge. So this is adjacent lah. 1, 2 adjacent, 1, 3 adjacent, 1, 4 adjacent, because it's connected by an edge. A path is a sequence of vertices that forms a path of length n1 if there exists a path, there exists an edge between vi to vi plus 1, whereby the minimum number of nodes is 1 up till n. Okay, so this is an example of a path. Okay, VEDC, VEDA, that is an example of a path. A simple path basically is where all vertices in that path are distinct, meaning there are no same vertices. So BEC is the same. Okay, so a cycle is not a cycle is another example, okay, of a simple path, because why? A, C, D, these are all distinct vertices. Okay, but the thing is that the last vertex is the same as the first vertex. So if you take A as the first vertex, so it's A, C, D, A. So the last vertex is a first vertex as well. So that is a cycle. So next we look what is a connected, disconnect, and a complete graph. So all vertices in this graph are all connected. So it's called a connected graph. This is what we call as a disconnected graph because these two nodes here are not connected to this graph. Basically, there's no edges for these two vertices here. Right? This is a disconnect graph because they are vertices that has no edges on them. So this is what we call as an isolated vertex as well. No edges means isolated. Okay? A complete graph is whereby every node or vertex is connected to every other vertex. So this, you see, this is connected to all the vertex. This is connected to all the other vertex. All right? So this is what we call as a complete graph. Now, what do we call as a degree of a graph? So when you talk about degrees, right, there's the main concept is the degree. Okay, but the degree can be broken down into in degree and out degree. But in degree and out degree, you need arrows. Okay, so we're going to look at that after this. So this is an undirected graph. So the degree of vertex V is the number of edges connected to V. So if you look at the degree, the vertex I here, what is the degree of vertex I here? It is basically 1, 2, 3, and 4. Because it is the number of edges connected to V. That is for undirected graph. For directed graph, it is the summation of both out degree and in degree. So what is out degree? So if you look at C here, the out degree is the edge coming out of C. So there's only 1, so you get the value 1. The in degree is basically the edge going towards C. So there's 2 here. So 2. What is the degree of vertex C? It is in degree plus out degree. So it is 2 plus 1, which is 3. If the degree of a vertex is 0, it is called an isolated vertex. If the degree of a vertex is 1, okay, this one in this case here, is called a pendant vertex. Okay, so the sum of a degree of each vertex is equal to 2 times 8 edges. So here means basically it's going to always be a positive number. All right. Okay. So how do you represent a graph? Okay, there's two methods. One is using adjacency matrix. So you must know how to convert this graph here into an adjacent matrix. Or there's another way, you present this graph here in a linked list. Okay. So let me have a look here. Okay, it's here actually. All right. So for example, if this is a vertex of a graph, okay, and here must be more than 0. All right. The adjacency matrix is represented in a 2-dimensional matrix. All right. So this is for a directed graph. Okay. So 1, 2, 3, 4, 5 is all the nodes. So here there's 1, 2, 3, 4, 5 as well. So up here is 1, 2, 3, 4, 5. Okay. So please download the new lecture slide. In the old one, that's wrong. So O1, it should be O1, 2, 3, 4. O is this one here. 1, 2, 3, 4. So it's both horizontal and vertical, yeah? So here, the first pair is 1, 2. So 1 is here. So 1, 2, you give 1. 1, 4, you give 1. 2, 5. 2, 5, you give 1. Okay? If there is no connection, you give 0. Alright? Same with this one. 0, 1 and 0, 3. So 0, 1 you give 1, 0, 3 you give 1. The others you give 0 because there is no connection. So next is representing the graph in a linked list. Okay? So the linked list you have to basically you have to represent the vertex and the link. Alright? So the formula is basically the same here. While you have a graph, you have vertices, n must be more than 0. Okay? But how would you represent it in a graph? Okay? So it's this one here. Because they are n nodes, we use an array A of size n such that AI is a reference variable. So it's a reference variable, that means a pointer pointing to the first node of the linked list containing the vertices to which VR is adjacent. Alright, so it's a reference variable pointing to the first node of the linked list. So here, 0, 1, 2. Okay, so you see, 0, 3. And then you have the connection 4, 3 and 1, 4. So we go for 0 first. 0 points to 1 or 0 points to 3. Sorry, so I said 0, 1, 2. Should be 0 points to 1, 0 points to 3. So 1 is smaller than 3, so you represent it. This one here, okay. AI is a reference variable to the first node of the linked list containing the vertices to which V1 is adjacent. So 1, 0, okay, is pointing to 1, okay, and it's also adjacent to 3. So 0 points to 1, points to 3. After that, nothing anymore, so it points to null. 1 points to 2, 1 points to 4. So you have 1 points to 2, and then points to 4. Okay, because these two are adjacent to 1. 1 and 3 is adjacent to 0. Can you guys see that? This one and this one here. Why this one points to null? Because it doesn't point 1 here. It's not adjacent to any other matrix. So next will be 2 points to 1 and 4. So 2 points to 1 and 4. 3 points to nothing. So it points to nothing. 4 points to 3. Points to 3. 3 points to nothing. Okay. Any questions? So this one is actually the same. So I'll just do a few first here. Have a look. So 0, 1, 0, 5. So 0, 1 and then 5 points to nothing. Next, you see the order. Pay attention to the order as well. Yeah? See, the order is 0, 1, 2, 3, 4. The order is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So next should be 1, 2, 1, 3, 1, 5. So 1 points to 2, points to 3, points to 5, 5 points to nothing because 1 does not point to any other node. Okay, next we look at the abstract data type for graph. So you can see the implementation to check whether the graph is to create a graph, to clear a graph, to print a graph, and how to traverse the graph. There's two types, depth traversal and breadth traversal. Okay, and then to find the maximum size of the graph. Okay, so this one you have to the implementation. Please look inside your textbook. So now you're gonna look at how you traverse a graph. There's two types, depth first and breadth first. So to present a data, to present a graph in the computer memory, the data structure is either using matrix or linked list. To traverse the graph, there's two methods, which is depth first search or breadth first search. Okay, so for depth first search, it is similar to binary tree pre-order traversal. So the main idea is to go as far as possible from a vertex before backing up. Okay, so let's look at the algorithm. You get a vertex, you mark it as visited. For each unvisited vertex U adjacent to V, you're going to repeat this process. So you see, U here is being passed back to this function DFS. Alright? And then you're going to create an empty stack. Okay? And then push V. So V here is a vertex. Okay? As long as it is not empty, if no unvisited vertices are adjacent to the vertex on top of the stack, okay, not adjacent to the vertex on top of the stack, you pop it. Else, you're going to push, alright, the vertex U into the stack again. So what is the concept of stack? Is it LIFO or FIFO? Rebecca? So it needs the use of implementation of stack. So Rebecca, are you there?
Yes. Yeah.
What is it, LIFO or FIFO?
Come again?
Is it LIFO? The concept of stack, is it LIFO or FIFO?
FIFO.
Have a look
First
at your stack.
in, first out.
Stack. LIFO. Last in, first out, not FIFO, yeah? Q is first in, first out.
I confused with that.
So please brush up your, that one very important, yeah? That is the first concept, yeah?
Okay,
Okay.
sorry, sir.
Apa? Okay, so you see, you visit V, alright? For each unvisited vertex U adjacent to V, nampak tak? You visit V first. For each unvisited vertex U adjacent to V, keyword here is U adjacent to V, yeah? Then U here, okay, will be passed back to the function. Okay? Create a stack, push V. So this is a vertex now. Push V, as long as it's not empty, okay? If there are no more adjacent vertex, then you pop. Else you keep on pushing to the stack. So you visit A, you push into the stack. You visit B, you push into the stack. What is adjacent to B? F. So you push F into the stack. What is adjacent to F? H. So you push H into the stack. So you get H F B A. Anything else in the stack? In anything else connected to H or adjacent to H? Nothing. So if there are no more adjacent, what do? You pop. So where do you pop? You pop to the stack. So when you pop at the stack, it is last in, first out. So last in was H. So you pop H. Then you pop F. And then you pop B. Okay? And then when at A here, are there any other connected vertices? Yes. C. So you push C. Now, C, anything else connected? No more. Alright? So you pop C. Okay? Anything else connected to A? Yes, there is. D. So you push D. Next, push G. And then you push I. Anything connected to I? No. So pop. So what do you pop? Last in, first out. You pop I first. And then you pop G. Okay? And then you pop D. Okay? And then you finally left A. Anything else connected to A? Yes. E. So you push E. Anything else connected to E? Nothing. So you pop E. And then anything else connected to A? No. So you pop A. Then you have an empty stack. Any questions? Okay, so we go to the next one. Rebecca has raised her hand. Yes, Rebecca.
No, sorry, sir, I misclicked.
Oh, okay, all right. Okay, so this is another graph. Say you visit A. Then you go visit B. So you put inside your stack lah, B. And then you visit C, E. So you take the longest path lah. Go G, E. E cannot go back to C because it's already inside the stack. Alright? Cannot go back to B so it's already because it's already inside the stack. So you pop E. Or here you call it backtrack lah. So you go back to G. Okay? Now, when you go back to G, then you add F. Okay? F connected to anything else can go back to A because it's already inside the stack. So you backtrack, you go back to G. Okay? And then you go back to D. And then you go to H. Okay, anything else connected? No. Backtrack, go back to D. So you get this A, B, C, D. Then backtrack C, B, A. A got connected to I. So you go back to I. Then backtrack back to A. And then finally, empty. So that is depth first search. Any questions? So depth first search easy lah. You just go deeper. Every time you find a node, you go deeper. No more, you go back up. Breadth first search is different. It's opposite. It's not opposite lah. It goes following the level. So level 1, level 2, level 3. So what is breadth first search? So you explore the graph layer by layer lah. or basically level by level. Now let's look at the algorithm. For each vertex V in the graph, if V is not visited, add V to the queue. So what is queue now? What is the concept of queue? It is first in, first out. Okay, so visit each vertex in the graph. If V is not visited, add V to the queue. Okay, now mark V as visited. As long as the queue is not empty, okay, then you remove vertex U from the queue. Okay, you remove a vertex from the queue, and then you get the vertices adjacent to U. You take the vertex out from the queue, then you get the vertices adjacent to U. For each vertex W that is adjacent to U, if it's not visited, add W to the queue. Alright, and then mark W as visited. So, you look at this graph, A. So, see, it says for each every vertex V in the graph, if V is not visited, add V to the queue. So, A, you add to the queue. Okay, so Q is from front to rear lah. So from front to rear, so you add Q A here, and then what is adjacent? So you see, while the Q is not empty, okay. Now for each every vertex in the graph, if V is not visited, add V to the Q, and then mark V as visited. Okay, so VA already visit. Now while the Q is not empty, remove vertex U from the Q. Retrieve the vertices adjacent to you. Okay, so this is if the, this is later lah. Okay, because why is it later? Because you see, you haven't go to each of the vertex in the graph yet. Okay, so you go to each every vertex in the graph. You go to B. You add A already. Okay, A got adjacent vertex, so you add in B. Okay, so you put here inside your Q B. And then you would add in C. And then you would add in D. And then you would add in E. Okay. Now, anything else you can add? No. Okay, so we will put B, C, D, and E. Now, while the Q is not empty, remove vertex U from the Q, retrieve the vertices adjacent to U, and put every vertex that is adjacent to you, alright, you add it to the queue. So you already put B, C, D, E. Okay. Now anything else that is adjacent to A, no more. Okay. So now you remove vertex U from the queue. So remove what's inside the queue. Inside the queue now you have B, C, D, E, A. So you remove B, okay? Then you replace it with what is what. So you remove U for each vertex W that is adjacent to U. So B, you remove what is adjacent to B, F. So F you have to add to the Q here. Like this one. Okay, this one here. So E, finish. So inside your stack is B, C, D, E, A. Remove B, replace it with a vertex adjacent to B, which is F. Okay, so you will add in F. So inside your Q here, you would have the value C, D, E, F. Okay, you baru letak ni. Okay, and then what happens? Anything else adjacent to B? No. So you remove C. So delete C. Anything adjacent to C? No. So you go to D. So you remove D. What is adjacent to D? G. So you will add in G. So you get E, F, now G. Okay. Now, what happens? You remove what's there inside the tag is E. So you remove E, have no adjacent vertices. So you just remove E. So left inside your Q is F, G, A. Now F, okay, so inside your Q here got FGA. So now what do? You remove F. Okay, anything else adjacent to F? Yes, there is H. So delete F, add H. So GH. Then next you remove G. Okay, and then you add in H. I. So you get delete G, inside it is H, A, so you put I. Okay, so you put H, I. Okay, now what is inside the Q? Inside the Q now you have H, I, A. H now. Any adjacent matrix? No, so you delete H. I, any adjacent matrix, you delete I. Finally left A, and then you delete A. Alright? Any question for breadth search? So breadth search, you go level or layer by layer. Alright? So this is a summary for graph traversal. For this your normal graph. So breadth first, why this one should be, okay, I go depth first search lah. Follow your slides. So depth first search, 1, 2, you go depth, then you go back up. Okay, then you go depth, then you go back up. So breadth first search, you go layer by layer by layer from left to right. Okay, depth first search is also left to right, yeah. So next is the concept of weighted graph. So weighted graph, when you present in your adjacent matrix, is the same. Okay, like you punya directed graph or undirected graph, just that you put the weight value in. All right. So what can the weight be? What does the weight represent? So it can represent physical distances between two vertices. Okay. So time taken from one vertex to another vertex, or the cost of traversal from one vertex to another vertex. So how do you represent the weightage? So the weightage here is basically given on the edge. Okay. So this is the weightage lah. This is the vertex. Okay, I and J. So this is the weightage. If there is a weightage, put in the weightage. If there is no weightage, then you put as infinity. So there's no edge lah from VI to VG. Here there's an edge whereby the edge will given the will be given the weightage. So here, so you have A, B, C, D. You have A, B, C, D. Okay. So A is 0, B is 1, C is 2, D is 3. The weightage is the one on the edge lah. 8, 6, 9 here. So A, B, the weightage is 8. Okay. B, A, the weightage is also 8. B is also connected to C, so you have 9. And then you have C connected to D, 9. And then you have D. So D connects to A, whereby you have weightage 6. So the others, no edge, you put as infinity. For linked list implementation, A, B, A, D. Okay, weightage is 6 and 8. But we follow the node, so you have A to B and then A to D. So A points to B, points to D. The difference between just now is that you put in the weightage value. So B, you put in the weightage 8. Up till D, you put the weightage 6. Now B to C. So B, there's to C and there's to A. Alright? So B to A, weightage 8. B to C, weightage 9. Make sure you end it with an empty pointing to nothing here. Okay? So here means at the end here is none. So inside your lecture slide, please correct this one as well. It's supposed to be here. Okay? So here, if you represent it in a matrix, alright, adjacency matrix here. So got connection, you put the value in, put the value of the weightage. No connection, you put the value -1. So here, 1, 2, okay, you give the weightage 5. 1, 3, you give the weightage 3. Okay. The others, you give the value -1 because there's no connection. Now, you also have 4, 1. Oh, you only have 4, 1. So you go 1, 2, 3, 4. 4, 1, you give the weightage 2. Else, you give value -1. 3, 4. 3, nothing else. Right? So 3, 4, you give the value 4. The others all -1. So if you were to represent it in a linked list, okay, so 1 is connected to 2 and 3. Okay, so 1 connected to 2, connected to 3. When 1 connected to 2, the weightage is 5. So vertex weight. Okay, so the weight is 5. 1, 3. Points to 3. What is the weight? 3. So this one, the next. So the next node here will be the weight. Okay, 2 connected to the vertex 5. So 2 connects to vertex 5. What is the weight? 7. So you put 7 here. For Rizwan, you're already late ready to the class. So shortest path algorithm. So for shortest path algorithm, we're going to look at Keystroke algorithm. For the implementation, you need to look, you can find inside your textbook. So this is just a brief introduction. Okay, so you basically want to find the shortest path from S to any other vertex in G, in the graph G. All right. So to find the shortest path is a path with the smallest weight. So there are two types of graph: unweighted graphs and weighted graphs. So how do you determine the smallest weight? For unweighted graphs, that means there's no weight lah. It is the number of edges in the path. But for weighted graph, it is the sum of the weights of all the edges in the path. Okay, so for unweighted graph, number of edges, but if it is weighted, that is the sum of all weights of the edges in the path. All right. So to find the shortest path, we use Keystroke algorithm. All right. For Keystroke algorithm to be implemented, all edges must make sure there's no non-negative weights. All right, and the graph must be connected. All right. So this is an example of Keystroke algorithm. So here it says that the shortest path would be so the value of the age is from 1 to 6. The nodes, okay, so shortest path is 1, 2, 5, 6. Okay, so it's the sum of the weight here. So for Keystroke algorithm, you just need to be aware to find the shortest path. An example of shortest path algorithm, it is we can implement using Keystroke algorithm. So Keystroke algorithm, if I'm not mistaken, you'll be learning it in detail in AI topics. Okay. But there may also be in network topics as well. Okay, that one I'm not sure. But for AI, there is a topic on Keystroke algorithm or AI or expert system. All right. So for this class data structure, you just need to be aware lah. Shortest path algorithm for graph, you employ Keystroke algorithm. Okay, but we're not going to look at it in detail. So for graph, basically, you need to know what are the basic concepts of graph. How you represent graph in computer memory, there's two types, adjacency matrix and linked list. What are the graph traversal techniques, breadth in and depth in? Okay, and you need it to know how it works. And then you look at the abstract data type for graphs. Any questions? Okay, if there is no question for this lecture, okay, then if you have question, can you guys ask in the lecture or not, please? If chat, I easily miss it because I'm teaching. It's hard for me to look at on the chat.
Sir, Nur Shahira asks, what's the situation where we need to apply graph on programming?
Number, representing numbers in a tree, right? And then finding a number. All right. So what kind of what is types of number? Shortest path. Okay. So if you have this type of basically if you represent this for distance. Okay. Imagine this is location to Kuching. Sorry, not Kuching. Kuala Lumpur. I'll take example for Kuala Lumpur. So you go your LRT map, right? And then you have the distance. So you can compute this and put it inside a graph. Graph, how you represent it in the data structure, you can use adjacency matrix or you can use linked list. And then using shortest path, okay, if you want to find the shortest path, you can employ Keystroke algorithm. Alright, if you want to search for a particular location, a node, okay, then you can employ depth first search or breadth first search. So here, Kuala Selangor, you give the unique ID 2. Sorry, not Kuala Selangor, Sumanjaya, you give the unique ID 2. Ampang, you give the unique ID 3, for example. Alright, then this weighted average here would be your punya jarak or the distance. Okay. Is that clear, Nushaira Ibrahim?
Yes, sir.
Okay, boleh tanya. So sometimes bila you tulis kat chat, I tak perasan. Kalau I tak perasan, tolong tanya lah. Because I tak nampak chat ni yang saya buka. Okay. for graph, there's no lab for graph. But however, can you guys please look at announcement on Thursday morning or tomorrow? But tomorrow, please check again Thursday morning. I think I'll post an example of graph programming. Okay. If no question, that's all for today. So please check your announcement tomorrow, yeah, by 5 p.m. or Thursday morning as well. Okay. Bye,
Thank you,
everyone.
sir. Thank
Okay.
you, sir. Bye.
Okay. Bye-bye.
Thank you, sir.
Bye-bye. Bye-bye. Please check announcement tomorrow before 5 and Thursday morning as well.